About right? Right, ready to go. Okay, good evening, ladies and gentlemen. You recall here last month that we talked about ground-based telescopes. And we said there was two key advantages of having a ground-based telescope and one big disadvantage. The two advantages were they can get as big as engineeringly you can get them as you want to and how much money you've got in your back pocket. And of course, that is the most important specification with any telescope. How big is your telescope? How big is your aperture or your primary mirror? The bigger the diameter of your primary mirror means you can get a much brighter image and finer resolution with much more detail. So you get bright, detailed images with large telescopes. And when you're on the ground, you can build them, yep, as large as you can afford. The other big advantage is they can be serviced and updated with modern technology. You can change the spectroscopes over to a new spectroscope, the latest one that's come out. You can take advantage of new technology. We saw how the Keck telescope embraced adaptive optics, whereby it counted the mirror adjusts itself, I think it was about 2,000 times per second to a precision of 9 nanometers. The primary mirror is constantly adjusting itself to the atmosphere, the turbulence in the atmosphere. So those are the sort of things you can do with ground telescopes. The big disadvantage with ground telescopes, however, is you're still on the surface of the Earth. You've got a big chunk of atmosphere above you. And the atmosphere causes turbulence and distortion of your image that causes the flickering, so to speak. The other thing, of course, is your atmosphere, as you're about to see, blocks out most of the light, electromagnetic radiation that's coming to us from the universe, from all sorts of wide range of astronomical objects and processes, and a whole range of wavelengths. Most of that is actually blocked by the atmosphere. So there's a big downside to being still on terra firma. So it makes sense after talking about that, well, let's move on, let's talk about space telescopes. So that makes sense, so I dug into it, and it's a huge topic, so I thought let's just split it in two. So we're going to have part one now. Part two will be early next year, so I think the quiz next month. Can't forget the quiz. Okay, so astronomy pre-1960s, this is pretty much what it looks like. These big domes up in the mountains and so on, and you're recapping that the locations for these big domes were remote locations, where you're away from sort of civilizations or cities, if you will, so it's away from light pollution. For radio telescopes, they like to get away from all the chitter-chatter and sort of jibber-jabber of microwave ovens and radio stations, TV stations, mobile phones and so on. So you want to get well away from other human beings, essentially, so I can understand. And the other thing is the sites are very elevated, they're high up. And of course, the advantage of being high up, the higher you go, two things. One is your air is colder and it's thinner, which means that you're getting less turbulence. Turbulence is caused by with heat rising, causing little cells of air to rotate around and getting little refraction going on of light as it travels through those cells. So if you're getting up high, the air is colder and it's thinner, so you've got less refraction of light going through that atmosphere. Less distortion and less turbulence going on. Of course, the other thing is the air up there is dry. If you get above about 3,000 metres, you're above about 90% of the Earth's atmospheric water vapour. The water vapour is heavy, so it tends to hang low. And of course, we learned from last month that water vapour absorbs infrared wavelengths of light. So if you want to get above as much water vapour as you can, that's why these guys are high. If they're up to, I don't think that Wilson's that high, but a lot of those places are, and they're above 90% of the water vapour, so it opens up a lot of the infrared part of the spectrum. So, 1960s onward, technology of rockets started advancing, and the beginning of the space age. So suddenly you could get a telescope up above the atmosphere, away from all that disturbance, distortion, turbulence and so on, above all the water vapour. So 1965 onwards, over 80 space telescopes have been launched. Over 80 of them. There's a few big famous ones which we're going to sort of talk about briefly. So you might say, well, what's the big deal? And as I mentioned, it's all about a lot of it is about the atmosphere absorbing different wavelengths of light. So I thought it would be nice to take a step back and just review some of the stuff we looked at last month. And this diagram is quite nice because it just shows you here the wave pattern of light. And light is best thought of as waves of electrical and magnetic energy just self-propagating through space. And it comes in a range of wavelengths and a range of associated energy levels. This diagram shows quite nicely, at this end you've got gamma rays, which is light, electromagnetic radiation at really short wavelengths, high energy. Just below that you've got X-rays, then you've got the ultraviolet, and you can see the wavelengths getting longer and longer, and the energy levels of each photon of light is dropping. Here's the little visible light that we see here. And it's no coincidence that that is the light that we see in. It's our sun, our star, emits most of its radiation between about 400 and 700 nanometer wavelengths. And of course our eyes have evolved and adapted to make the best out of that, and we're most sensitive to that. Then the infrared, you can see the wavelengths getting longer at microwaves and into radio waves. And you'll see here how the range of wavelengths is quite incredible. 10 to the minus 5 nanometers. So that I worked out, that's 1/1,000,000th of a centimetre. 10 to the minus 5 nanometers. You get a millimetre, or centimetre rather, you get a millionth of that, then what are those? You get a millionth of that. And that's the length of the wavelengths of these gamma rays. At the other end, look what you've got here. You know, you're dealing in kilometres here. There you go, that's up to a kilometre, 10 to the 3 metres. So the wavelengths of this end, you're dealing in kilometres. So that's a whole wide spectrum of different wavelengths. As I mentioned, visible light's 400 to 700 nanometres. So this afternoon, let's put that in something we can understand. So 100 nanometres is 1/10,000th of a millimetre, to give you an idea of the size of the wavelengths. So we're looking at 4 times that, up to 7 times 1/10,000th of a millimetre. That's the wavelength that our eyes have adapted to become very sensitive to. So in this diagram here, once again, just a bit of revision, this shows how that's the atmosphere and that's how much wavelengths are getting through, the atmosphere penetrating through. You'll see all the gamma rays are completely blocked by the atmosphere, none get through, no X-rays get through, no ultraviolet get through, but a little bit of ultraviolet gets through, hence our skin cancers and sunburn. But look, the visible light is the main part of that spectrum. See how small it is against all the rest of it, the range of wavelengths. The visible light is pretty much the only range that mostly gets through. Infrared's a bit patchy, and as is the microwave here, and then the later microwave and the radio waves get through to about 10 wavelengths, to about 10 to 15 metres. But you can clearly see from there, most wavelengths of light, where all the action is happening up there in the universe, is actually blocked by our atmosphere. So you can see the big advantage, the big wide of one of these space telescopes up there. So, tonight I'm going to show you that space telescopes are a revolution in astronomy because they're able to detect light across a broad wavelength range. We saw they're above the atmosphere, they can see gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves. They don't suffer atmospheric distortion, turbulence, but they do have limitations. I think it's not all rose, everything life's a trade-off. They are restricted by cost and aperture size. So remember I said the advantage of ground-based telescopes, they can become large and diameter size is crucial for telescope specs. When you see a rocket get launched into space with whatever payload it's got, 85% of the weight or mass of that rocket that you see go up the pad is fuel just to get up into orbit. That's how costly it is to launch anything into space. So you've really got to keep the size of your of whatever you're launching up there down. And they cannot be really maintained and upgraded. Pretty much the Hubble's the only one that's been able to do that. But otherwise, they're not accessible. New technology comes, new spectrographs and so on. You can't go up there and change them like you can with the ground space. So that's the big trade-off. So that's what we're going to cover tonight. Okay, now part one, I'm just going to give you a little bit of a roadmap of part 1 and 2. So I'm going to outline 6 famous telescopes. We're going to focus on 3 tonight, and then 3 for part 2. We're going to talk about the concept, how images are combined and colorized to give you a better idea of what's going on out there, and to make the pictures in your book and the internet pages nice and glossy and colourful. I thought we'd just get a case study. Matariki is always a topical subject for here in New Zealand. We're going to look at that. You always see it in just the 7 sisters. Let's look at it in multiple wavelengths and actually have a deeper look into Matariki. I'm going to introduce you, show you how space satellites are used for the astrometry, to field of astronomy that deals with the position and the size of various objects. I'm going to then just recap some of the disadvantages of space telescopes, and then we'll look at a bit of a hybrid, an airborne telescope. So, part 2, so next year we're going to revise part 1 like I did today. We'll always recap the main points. Then we're going to look at the other 3 telescopes. I thought it was a good opportunity to talk about the satellites that are observing the cosmic microwave background, which we'll talk about, of course, and some short movies on these things. I've actually, this afternoon, thrown in 3 short movies on this too. Okay, so 6 famous telescopes. You'll know that, maybe, don't you? Yeah? Hubble! Yep. Absolutely. This one hasn't even been launched, but I'm sure you know it by name. James Webb. Who knows the name of this one? Chandra. Yeah, yep. I'm studying it at the moment. I swim in falling apart bolt by bolt. How about this one here? That's the Spitzer. Sorry, that's the GALEX, right? And that's the Spitzer there. And that's the Fermi gamma ray. So let's see which one. So here they are here. That's the 6 telescopes. And I've ordered them in. There's the Fermi that's dedicated to gamma rays. The Chandra Observatory that's dedicated to X-rays. Galaxy Evolution Explorer, GALEX, Hubble for ultraviolet and visible and some infrared. Spitzer that's dedicated purely to infrared. And then the James Webb, which is going very much further into the infrared. So tonight we're going to focus on these 3, and those other ones we'll talk about next time. Right, let's move ahead. So I put here, let's start with ultraviolet light. Observing the universe in ultraviolet. I just put here to remind you where it is. So it's just above, there's visible light, and it's sitting up above there. You can see most of it does get blocked by the atmosphere. So, the Galaxy Evolution Explorer, GALEX. Not a lot of people have heard of it when you ask them about it. So, it's this satellite here. Its diameter is 50 centimetres, so it's 30, so it's about yay big in diameter. So, it just gives you an idea of they can't make big space telescopes. They're expensive. It operated for 10 years from 2003 to 13, put it into low Earth orbit, and its key thing was, to study objects emitting lots of ultraviolet light. In particular, it was really good for measuring star formation rates in distant galaxies. How many times have you picked up a book or looked on the internet or read something in a paper and it said that star formation in a galaxy peaked at about 5, and the universe was about 5 or 6 or so billion years old. Star formation peaked and it's been declining since. And you think, how do they know that stuff? GALEX, the bottom line is. So what is very, very sensitive to measuring ultraviolet light, very faint ultraviolet light, and measuring the distance to the galaxy at which it's measuring that ultraviolet light. So you might say, well, here's that time in the star formation. So when you get large molecular clouds, you get a whole stack of stars all forming in those clouds, what stars occur first? What stars develop and evolve the quickest to get up and start lighting themselves up? The big massive stars, right? They're the first stars that light up. The other ones are slow, long behind. What do those large massive stars that light up early, what do they emit in copious amounts? Ultraviolet light. Our star's a medium star. It mainly is the visible light. It gives us a little bit of X-ray in its atmosphere, predominantly visible. These big mothers, these big OB stars that get lit up very, very quickly early on in the star formation process, emit almost all their energy in ultraviolet light. So it makes sense. If you can measure, look further back in the universe in time, distance in time, find a galaxy, measure how much ultraviolet light's being emitted from that galaxy, work out its distance, the star formation rate, and match that distance up with the age of the universe. That's how they tell you, hey, this is the way star formation rate went up and it's peaked and coming back down. GALEX has done that. It's really cool how they launched it. So this is it here. And see, what are they doing here? They're strapping it to a rocket, to a Pegasus XL rocket. In fact, that's interesting. It is interesting. What are they doing here? Now they've got the Pegasus, that's the satellite there, here's the Pegasus rocket. They're now strapping it to the belly of the Lockheed Stargazer plane. Check that out. How crazy is that? They're going to launch this baby with this. It's an interesting plane. That's the Lockheed L-1011 plane, TriStar plane made by Lockheed. NASA bought this, one of them in 1994 and modified it to launch these Pegasus rockets. And I think they launched about 40 Pegasus rockets with various satellites, weather satellites and so on, but GALEX was one of the ones that it launched. So not every day you see something like that, a satellite being launched by that method. Okay.
I think NASA got them cheap second hand because the planes that you go back to the late 60s, early 70s.
Yes, yeah, typically, yeah. I think it was Alistair said, oh, heavens, so fair. It's only whatever year you said. I said, that's all NASA can afford. Give them a break. Right? Yeah.
She's clapped out.
Yeah. Okay, so let's
Drop on my mark. 3,
2, 1. Go for release. And drop Pegasus is away. The mission of the Pegasus rocket was Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
Isn't that cool? This, as you can see here,
the inaccurate
that's
system is working properly.
how they launch
Flight
GALEX.
vehicle during stage 1.
Okay, so it goes on to listen orbit. It's pretty cool, huh? Yeah. Okay, so how big's the field of view? And this is one of the really key features, really a cool feature of GALEX. It's field of view, in other words, in one single shot, how much of the sky does it cover? 1.2 degrees. You might think, well, how big's that? The full moon is about half a degree across from here to here. So it gives you an idea of the field. It's much bigger than the size of the full moon that it covers in one exposure. Another interesting thing is sort of little interesting miscellaneous things they're able to observe, and this is a wonderful example of when you start looking at other wavelengths, what you can see in a seemingly pretty straightforward sort of scene. The star Mira sits here, it's in the constellation Cetus, and it's an older star, it's a fairly unstable variable star shedding large amounts of hydrogen, and this is just a picture where it is in the sky. There's Orion, there's Pleiades and Taurus there. And here's some Hubble pictures. That's a picture from Hubble of Mira in visible light. That's what it looks like in infrared. But when they shine GALEX at it, they got one heck of a fright. Look at all this. This is what the X-ray. So here's the star is right there in the middle. My pointer's getting a little bit tight. So right there is the star, and you look at this huge big shock wave here with all the nice huge long tail. That tail extends to 13 light years. When you look at an X-ray, what on earth has caused that? Twofold. One is, as mentioned, it's a pulsatile variable star, it's a bit unstable, it's shedding large amounts of hydrogen from the outer envelopes, and it's travelling at a very unusual high speed through the galaxy. 130 kilometres per second, Mira is zipping through the galaxy. So as it's shedding off its hydrogen, that hydrogen is ramming into all the interstellar gas and dust ahead of it, and it causes that shock wave, and it's like a big trail right behind it, 13 light years across. They estimate from here to here it's taken about 30,000 light years for that to have formed. That's a beautiful example of how you look at something, just an average looking star, wham, look at it in X-ray, look at what you see. It's just a whole different process, astronomical process going on. Gives you a lot of insight into the star. Okay, now just also, this is just another little video. This is a couple of scientists who are involved with GALEX. They sum it up quite nicely. It's nice to break things out with a movie. So they talk about GALEX and what they're doing with it.
GALEX is a NASA Small Explorer class mission. It's an Earth-orbiting space telescope designed to observe the ultraviolet. It's not very big. It's only about 50 centimeters in diameter. It was launched in April of 2003, and it orbits about 690 kilometers above the Earth.
It's an international collaboration between the United States, France, and Korea.
It's managed by NASA and JPL as well as Caltech. The purpose of the satellite was to investigate the ultraviolet sky, to survey the entire sky for the first time. It's called the Galaxy Evolution Explorer because the purpose was to explore the evolution of galaxies from present to at least halfway back to the beginning of the universe. In addition, GALEX offers the opportunity for guest investigators or guest scientists to use the telescope for their own investigations into UV astronomy. So the ultraviolet is a portion of the spectrum that is bluer than what our eyes can see. It's just beyond the edge of our blue edge of our sensitivity. It tends to be absorbed, a lot of it that we're interested in is absorbed by the upper atmosphere. So that's why we were motivated to put a telescope in space to explore the ultraviolet universe.
The reason why we observe it is because we're looking for star formation. And young stars, which tend to be massive stars, emit most of their light in ultraviolet. So if we want to measure the star formation of galaxies, the best way to do that is in the ultraviolet. We've been finding star formation in some really unusual places. M83, the nearby spiral galaxy, is a perfect example. We see star formation extending out 4 times the optical disk of this galaxy in places where we had no idea star formation was occurring at all. We also find little hidden treasures. The ghost of Mira is another nearby galaxy.
So in the optical, all you can see is what appears to be an old dead galaxy. In the ultraviolet, the star is much fainter and the galaxy starts to shine forth. What we see in the ultraviolet is that, in fact, there's ongoing star formation, and it's not anywhere near as dead as we thought it was. Another interesting place is some primordial gas that we found in a ring around a group of galaxies in the constellation of Leo. People have known about this primordial gas, but they've been unable to find star formation in it. GALEX, with its sensitive UV detectors, was able to definitively detect ongoing star formation in this ring.
A little closer to home, GALEX also observes stars. Now, this was not the primary mission of GALEX, but we actually can't help but look at stars in our own galaxies. We have to look through the galaxy to observe the galaxies beyond our own. And this has also led to some great surprises. A perfect example of this is Mira. Mira is a very old, what they call red giant star. We didn't expect to see this object in the ultraviolet at all. It turns out not only do we see the star, but we see it plowing through space at an amazing speed. And in the process, it's shedding off material and leaves a tail very much like a comet behind it.
People have been imaging and studying this star for 400 years, but until GALEX looked at it in the ultraviolet, we didn't know that, in fact, it has a tail streaming behind it that's 13 light years long because of this motion and because of the shedding gas. Another interesting thing that we found was an interacting binary star, 2 stars that share matter between the 2 of them. And we see some incredible structures that basically are the traces of explosions that happen because of this interacting matter. And GALEX was the first satellite, first chance to observe the traces of this explosion. So GALEX has a lot to look forward to. We are observing the sky in certain places. We're going back time and time again. And this allows us to determine for the first time the sort of general variability of sources in the ultraviolet. We also are archiving all of our image data so that we can keep track of what's been observed and study objects in detail. This archive is going to be publicly available. It is currently publicly available through the web to anybody. So there's a tremendous amount of data being generated by GALEX. The images are very large, and it's impossible for professional astronomers to actually put their eyes on every single image. So it's an opportunity for the general public to download the images and look at them, and maybe you'll discover something like Mira.
Currently, we've imaged about 3/4 of the sky in the ultraviolet at various exposure times, and we continue to fill in regions as the mission continues. This is going to be the standard ultraviolet database for the next decade. There's a tremendous amount of data, and there are so few eyes to actually look at it. So go out there and make your own discovery.
Yep, so there you go. So that's satellite you may not have heard before, and you now see how important it is. It's essentially creating the database to mine that anyone can go out there and mine, so you can rush home tonight to do that. I was quite interested, they looked at a galaxy that they thought was a pretty dead galaxy, long spent all its action. They looked at it through GALEX. Woohoo, there's a lot of star formation still going on in the galaxy. You wouldn't have picked that up otherwise. So we're moving on to the visible wavelength, and of course the master of that, also a bit more versatile, is the Hubble telescope. And there's two key things about the Hubble telescope. It is large. Currently it's the largest space telescope. Primary mirror 2.4 metres. So what that sort of an area sort of gave big, sort of sweeping that sort of area. Now that's a large size diameter. That's actually larger than anyone's standards, 2.4 metres, even for a mediocre sort of ground-based telescope. So it's very, very large. The whole structure is about the size of an American yellow school bus. You see that Forrest Gump, was it? It's about the size of those there. And it's very versatile. Primarily it's the visible wavelengths, but it does extend right into the ultraviolet and into the infrared as well, what we call the near infrared. A lot of those ranges, such as infrared, being split into three, like near infrared, if that's visible, near infrared, medium infrared, infrared and far, and so on with ultraviolet. They tend to split them up. So this is quite happily that we'll look into the near infrared and also quite happily look into the ultraviolet light. So it's very versatile. It's large and it's versatile. It was named after Edwin Hubble, this guy here. We looked at most of his research in the early 1900s at Mount Wilson, the picture that we saw early on when we started the talk. In his honour, he was the first one to discover that the universe was expanding. It was about 1929 or something like that he observed that, and now it's called Hubble's law. Probably heard of that. So that's from him, his honour. So the Hubble telescope, because as I mentioned, launch one of those things, or any rocket you see on the pad, 85% of the weight of any rocket is just the fuel to get into orbit. So you think, well, how on earth did they get that bus up there? Space shuttle. So it was in the instrument bay of the space shuttle in 1990. They launched it up, put it in a low Earth orbit. Mentioned 2.4 metres, so it's large. What does that mean? It has bright images and it has detailed, high resolution images. And as I mentioned, very versatile. Arguably, probably one of the most sophisticated and productive scientific instruments ever built by mankind, Hubble telescope. So productive. In fact, I think the last shuttle mission I was servicing, NASA asked the astronomy scientists, the whole community, do you want us to spend one more shuttle mission? Should we go up and service the space station or do a science mission, or should we service the Hubble? And it was just unanimous. They got bowled over by the big response they got from the scientific community. For God's sake, you got one more shuttle. Get it up there and service the Hubble. Keep the Hubble going for longer. One of the most productive instruments ever produced. That's the just diagram here. See the little slither of visible light. So it's able to go into the ultraviolet and cover all the near infrared as well. That's a sort of suite of instruments that does that, which we'll talk about now. So what's under the hood in there? It's optical design. It's called a Ritchie-Creakin optical design, which most professional telescopes are. And it has its primary mirror back here. I've got a better diagram I'll show you, but it's nice when you see all this. Solar panels here. There's its aperture. The light comes in here, hits the primary mirror, bounces back up to the secondary mirror, and goes back through the back here to the instruments. I've got a better picture of that. I just thought I'd show you that one because it shows the full structure. So here we go here. Here's the light path. Hits there. Those of you who's a bit more technically minded, that mirror is a concave hyperboloid. So say spherical like that, paraboloids are spread out a little bit more, and hyperboloid a little bit further. So that sends the light, that's concave hyperboloid, sends the light this way, through here, these arrows here. And normally your focus point would be about here somewhere. So before the focal point, they put a convex hyperboloid secondary mirror sitting right here. That bounces the light through here, through a hole in the primary mirror, and behind there. It's called a passive running focus. That's the optical axis, a line running through there, so it goes right through the middle. All your main axial instruments are all sitting in here, and they have turns that see the light and doing their business with the light. It's also quite versatile. It has what they call little folding mirrors sitting in here. It also can divert the light So what they call these off-axial instruments here, which we'll talk about soon, line guidance sensors and the wide field camera 3. So that's the optical design of what's going on inside the Hubble. Let's talk about some of its instruments. So essentially it's got 2 cameras. This is currently what's going on. It's had a lot of changes, but it's currently got 2 main cameras, 2 main spectrographs. Remember, spectrographs are something that split the light up into all its individual wavelengths, which can tell you the composition, chemical composition of an object. It can tell you how hot it is. It can tell you how fast it's travelling towards you. So they're very useful. And it's got 3 interferometers, which we'll talk about. Actually, let's go back to this one's a lot bigger, isn't it? So the 2 cameras here is called the advanced camera for surveys. Here, that sits here. And the other one is the wide field camera 3. There has been 1 and 2. They upgraded it. I've got a lovely picture of the astronaut inserting the wide field camera 3. The advanced camera for surveys is made primarily in looks at things and records in visible wavelengths. And it complements quite nicely the wide field camera, which has got a nice wide field, obviously by its name, but also that's quite versatile. It'll happily take images, ultraviolet, visual, right through into the infrared. So it's quite versatile. The two of them work quite nicely together. Your 2 spectrographs, cosmic origin spectrograph, that's really, really sensitive, and as the name implies, cosmic origins, it's looking back, very, very sensitive. It's looking back to galaxies way, way, way back in the beginning of the universe. So that's very, very useful. And the Space Telescope Imaging Spectrometer is a more wide spectrum sort of thing. It looks, once again, visible, ultraviolet, and the infrared. And in particular, it tends to prefer a lot brighter images, which of course the Hubble telescope can deliver in 2.4 metre diameter. So those are the 2 spectrographs. Then it has 3 interferometers. It has 3 what they call fine guidance sensors. And they're really, really sensitive, and they're looking straight ahead where the telescope is pointed. And they do 2 things. One is that they act as a form of guidance. They work together, hence the term interferometers. All 3 of them work together. And they provide a guidance for the telescope to keep it with the gyroscope, to keep it exactly focused in one spot so there's no wobble. It tells also, it'll take a location of the star and help it remain focused and tell the telescope what it's actually looking at and where it's looking. Also, it's been paramount in the whole science of astrometry. In other words, looking at an astronomical object and determining the exact position of it, where it is in the sky, any possible movement from last observations, and how big an object is. That whole field is called astrometry, which we'll look at shortly. So those double purpose. So that really is the guts of the instruments behind the Hubble telescope as it is now. The near-infrared camera multi-object spectrometer, because it was near-infrared, it needed cryogenics. They had a problem with the cryogenics. That's pretty much in hibernation at the moment. Probably will not be used again. They used it initially, so it's not being used at the moment in the cryogenic problems. Oh, sure, yeah. Cryogenics means to cool something down, like liquid nitrogen or something like that, or liquid helium. You run something like that either around or through the instrument, and it cools it down. So, and what's the importance of that is when you look at something in the infrared, which is cooler than the light that we're seeing here, if there's any heat, there's infrared and heat, that's how we experience heat through infrared. So infrared and heat are very synonymous. So the instruments themselves generate heat, the electronics and so on, just the physical framework of them, they all generate heat. You don't want that heat. That heat is noise to the signal. If you try to look at it in infrared, so it heats the instruments nice and cool to reduce all the background infrared noise that's going on from the actual electronics of the machine itself.
When they first launched it and they had its problems, did they put a lens over it, or did they just change the back-end instruments?
Good question, Steve. So it's probably Hubble's infamous for its original problem with its optics. When it went up there, the primary mirror was out by just a fraction. But it was enough to distort it and cause astigmatism. And they essentially put a lens in it. It's called the COAC, which COSTAR. Yep, COSTAR. Essentially, they put a lens in front of it. Yep. They took out one of the instruments, I thought of having a whole talk on the Hubble, and I don't care a lot of stuff left right today. But yeah, they took an instrument out and they put the co-star over it, and the coaxial, but essentially it was a lens. They put pure speed.
So they had to remove that when they put the upgraded instrument.
You have to remove one of the axial instruments, correct, and sacrifice on the co-star, correct, yeah. And then they were away laughing. And sadly, because Steve, you've raised an interesting point that you often, so lay personally, we hear the word Hubble. And all they recorded at the Hubble, oh, wasn't that a big flop? Wasn't that a terrible disaster? Nothing ever came of it. No, that was just a small little speed bump early on. They well and truly got over that. It's just funny, isn't it? Sort of bad news is always the brightest thing. So the Hubble, yeah, is very large and versatile. And I've just got some pictures up here just for the pleasure of seeing them on the big screen. So that's the Hubble being released from the shuttle in 1990. That's our graphic and artist's impression of what the release would have looked like. The big arm, the shuttle arm looking down the bay. That's just a photograph of Hubble taken from the telescope. You see that? That's a shutter they put over if they had to, if they're pointing towards you. For example, you would not want to point the Hubble towards the sun. You know, wipe out all the instruments, they're too sensitive. So if there's any inkling of anything bright in the area, they shut it off. I'm led to believe, I didn't think they sit and people say, why don't they look at the moon or the Earth with that big and powerful? The Earth is too bright. They can at certain times look at the moon in certain phases. They wouldn't look at a full moon, but you can actually look at the moon at certain phases. But otherwise, that's what that's for. They do not want to look at anything bright when they're turning it around. There are your solar panels. Here's all your axial instruments sort of sitting back here. And your off-axial ones, like your double, the wide field camera 3 will be sitting here. Your primary mirror will be sitting about here, and your secondary mirror is up about here. So light's going in through here, hitting the primary mirror, back towards the secondary mirror, and then back through the middle. Put the Cassegrain focus to all the axial instruments about here. It's another cool picture. Panels, you can see how they can obviously get access to the panels. Hubble was serviced 4 times, it's been visited 5 times, one to switch it. The next one was to put the optical correction lens in, and then it's had upgrades to its instruments. So that's the exception to, that's the big advantage of being in a low Earth orbit, or low Earth orbit, still a lot higher than the space station. I think it's about 400 kilometres orbit, I think, remember rightly? Yeah, it was high, it's high, considered a high orbit for the shuttle, but in the big picture it's a low Earth orbit. They were able to service it. Here's that's the wide field camera 3 being installed. We would have taken the wide field camera 2 out and installed the 3rd camera. So this is a beautiful example of what 99% of space telescopes do not have the luxury of doing. This really is the exception to the rule, which makes Hubble just so brilliant. Now, how long is it? That's sort of coming up 30 years, isn't it? Coming up 30 years because it's about to be upgraded. That's the final servicing mission there. And that's the final release. Beautiful. Put this up here. This is all of Hubble's data, all its images are on this website. And I'll put that in the handout too, by the way. That's the work. You go to that website, you'll see all of Hubble's raw data, just as they talked about in the GALEX, those guys said. Look, the professional guys can't look at everything. A lot of the screens with computers and stuff, but amateurs can go digging around and mining through the raw data and get stuff if you like. So that should be on your desktop as one of your key bookmarks. Next to eltonjohn.com and astronomy.org.nz and catsrus.com. The other thing I thought I'd point out here is all raw data in astronomy is black and white, it's grayscale. It's just all data. Now, all your fancy spectrographs with all the colours spread out, all your fancy pictures of this and that, they've all been colorised. Astronomy is data. It's concerned with black and white, how intense a signal is, and it's all grayscale.
How do they steer the Hubble telescope?
Gyroscopes with your fine guidance sensors, yeah.
So,
and reaction wheels.
I was going to say, what's a reaction wheels full growth?
Yes, yeah.
How come Hubble's managed to keep going for so long?
Probably engineered by Germans, maybe. But yeah, you've got like it's gyroscopes and reaction wheels. Yeah.
The key part of Hubble was, with the other service, it was the gyroscope did slightly fail, but they started with 6, and they slightly failed, they can operate on 3. And so as I said, because they're in a service and they replaced them, that's the biggest problem now, is they're down to 3 now, I think it is? Yeah, they're down to 3, so one more goes and they have they can do limited operations on 2, but not really, because they can't put it accurate and they can't keep away from the sun all the time. So.
Yeah. And Kepler, that's been the nail in the coffin of Kepler, is the reaction wheels. Yeah. Another little famous image from the Hubble telescope is they've got a small patch of the sky that looked apparently black. It was just blank, it was just tiny. You get a grain of sand, hold it up to the sky at arm's length, you see a tiny, tiny speck of the sky. They picked a tiny speck of the sky in the constellation Phalanx, and it just stared at the multiple images from 2002 to 2012, just prolonged images, the couple of cameras there, and as they built the images up, this seemingly tiny blank bit of space, they looked the whole way back to something like, I think, about 13 billion years they look back. There's like 10,000 galaxies in that picture. So it gives you an idea of, just you see a blank bit of sky. If you look back through there, that tiny, tiny speck of blank sky, just focus on it, keep looking further back in time. 10,000 galaxies are identified through a long exposure. It's called the Hubble Ultra Deep Field.
So if I remember correctly, the field is if you hold a pinhead at arm's length, that's the field you're looking at.
Yeah. Amazing. Moving on to the infrared, just reminding us that these, as we just spoke to just a short time ago, these are visual wavelengths. The infrared is much weaker, longer wavelengths and much weaker.